Hello, my name is Mouna Safir, and I'm a PhD student in my first year at School of Computer and Communication Science at University Mohammed VI of Maghreb, and I will be presenting the paper entitled Byzantine Cassette Agreement that was written by Carole Delporte-Gallet, Hugues Fauconnier, and myself. Now, moving to the outline of this presentation, first, I will discuss the motivation of this work. Then, I will present the model we based our work on and some essential definitions. Next, the background of the work. Then, I will detail our solution with the algorithm part and then the impossibility result. Finally, I will highlight this work conclusion and future perspective. So, let's start with the motivation behind this paper. So, an important goal in distributed systems design is actually to construct the system in such a way that it can automatically recover from partial failures without seriously affecting the overall performance. In particular, whenever a failure occurs, the distributed system should continue to operate in an acceptable way while repairs are being made. It means that the system should tolerate faults and continue to operate to some extent even in their presence. So a system that fails is not adequately providing the services it was designed for. If we consider a distributed system as a collection of servers that communicates with one another and with their clients. So no adequately providing services means that the servers, or for example communication channels, or possibly both, are not doing what they are supposed to do. But the main problem is that the servers has to agree in a way or another, for example, to take a common decision, execute specific actions, or validate some commitments. Said another way, agreement problems lie at the core of distributed computing. The problem of consensus is perhaps the major problem in distributed algorithm, and it is one of the agreement problems. And it has a certain interest, both in practical and theoretical terms. So the problem of consensus can be quickly defined informally in the following way. It's a set of processes, each providing or proposing a value, and we need to find a distributed protocol in order to put all the processes in agreement on one of the values proposed initially. And the interest of such a protocol comes from the fact that if we are able to solve the problem of consensus, then we will be able to implement fault-tolerant services, and a fault-tolerant service can support crash. Means that a process stops working. And also a fault-tolerant service can also support Byzantine. And a Byzantine process may crash, fail to communicate, but also may deviate from its code. And the consensus problem is actually known as a particular case of cassette agreement, where in this case, K is equal to 1. Let's move to the model we used on our paper. So our system is made of n sequential processes that communicate. Our system is synchronous, and a synchronous system, we have the process, speed, and message delay are known. The execution is partitioned into rounds so that every process can send a message to other processes. The messages are delivered, and then every process computes based on the message just received. And the processes communicates with one another by message passing. And in our case, we will concentrate on the Byzantine failures model. So as I said, a Byzantine process may crash, fail to communicate, but also may deviate from its code. The Byzantine process may actually act as an adversary without any computational limits. One of the most important notions of our paper is the cassette agreement problem. The cassette agreement problem is a generalization of the consensus problem. The cassette agreement is formally defined by the following properties. First, we have the agreement property that says at most k values are decided by the correct processes. Then we have the validity property, and actually it is the most important property of the cassette agreement, and it says that if all the correct processes propose the same value, then no correct process can decide on another value. And finally, we have the termination property that says that finally or eventually a correct process will decide. Now we will move to the background of this work, and it's summarized in this table. Actually, we have two types of systems, the synchronous system and the asynchronous system. In the synchronous system, as we said, the process speed and the message delay are known. And in an asynchronous system, where we don't have any fixer upper bound on how long it takes for a message to be delivered, or for example, how much time elapses between two consecutive steps of a process. So in a synchronous system, if the failures are only crash failures, so it is possible to solve a T-resilient cassette agreement for any T and K in a synchronous system if T is less or equal than N, with T is the number of Byzantines and N is the number of processes. While in an asynchronous system, the condition we have is that the number of Byzantine should be less and equal to K minus 1. While if we have Byzantine failures, so for both synchronous and asynchronous system, the number of processes should be greater or equal to 2t plus t over k for the both systems. And in addition to that, the number of Byzantines in here should be less or equal to the number of agreed values. Let's take an example and let's compare the result we had before our algorithm and the results we have after our algorithm. So let's take n equal to 19, which means we have 19 processes. In this case, we have in the abscess, we have the number of Byzantines, and in the ordinate, we have the number of agreed values. So for example, if we take a tk points in this area, which is colored in blue, the cassette agreement is impossible to solve. While a point on the left part of the blue line, in this part, well, we can have cassette agreement algorithm with T Byzantine processes. So why? We have an important result that says that if we want to do consensus, the number of processes should be 3 times greater than the number of Byzantines. In our case, we have n is equal to 19, which means that the number of processes, Byzantine processes, should be up to 6. So if we can do consensus up to 6 Byzantines, then we can do any cassette agreement in our system if we have 6 Byzantine processes. And actually in this area, we don't have any results. We know that we can do cassette agreement, but we don't have any algorithm. Now So let's move to our solution. Our solution is this figure, and for tk points on the left part of the blue line, we can do the cassette agreements, and for tk points in the area colored in blue, the cassette agreement is impossible with T-Byzantine processes. So one of the area comes from the results of Bouzyt's paper, and this area, surrounded by green dots, it's from our results, and we're gonna see this later. And for a TK points with the red cross, those two, actually we don't know if the cassette agreement with T-Byzantine processes is solvable or not. Now we will present a T-resilience algorithm that solves the cassette agreement problem under certain conditions. So this is our algorithm. Our algorithm works in one round. Each process sends its own value to all other processes, and it receives from the other processes their values in the same round. Then we will have a condition. So if a process has received n minus t minus 1 values equal to its value, then by the validity property of the cassette agreement, the decision value has to be this value, which means his own value. If this condition is not fulfilled, well, it can decide on any value. And to avoid that many values are decided, we choose a default value in V for this case, and this default value is 0. So this leads us to have the following theorem that says that the algorithm we have solves T-resilience cassette agreement problem if for two cases. If n is greater than 2t plus 1, which means that if we have a majority of corrects, then the number of set agreements should be up to this value. And if the number of corrects is not, we don't have a majority of corrects, then we can do up to t plus 1 set agreements. So we will give a proof to our theorem. So we had two results. The first result is the case where we have a minority of corrects, and the other case where we have a majority of correct. So we will explain when we have a minority of corrects. The termination of the algorithm is actually obvious because we have only one round, and since we have only one round, so the processes will decide whatever happens to the system. For the validity property, we have that if all the correct processes propose the same value V, for example, each process will have at least n minus t identical values, because we will have at least n minus t correct processes. Then our algorithm says that if a process receives n minus t identical values, then they will agree on this value. So all the correct processes will agree on the same value. For the agreement property, we have if all the processors are correct, then if all the proposed values are different, they decide 0, since no one will receive n minus t identical values. And if there are n minus t minus 1 Byzantine processes, then t plus 1 correct processes may decide their own value. And if there are more Byzantine processes because of the agreements, then at most t plus 1 values are decided by the correct processes. And finally, if there are less Byzantine processes, there are at most t plus 1 decided values by correct processes. For the case where we have a majority of correct, you can refer to the paper for more details. Now we will focus on the case where cassette agreement problem is impossible to solve. So our starting point is the paper of Bouzyt, which demonstrates that if the number of correct processes in our system is greater than the k or equal than k plus 1, there is no T-resilience algorithm that solves cassette agreements when the number of processes is less or equal than this value. We complete the results when n minus t is less than k plus 1 and n, the number of processes, is less or equal than 2t plus 1. So if we have those conditions, there is no T-resilience algorithm that solves cassette agreements when the number of agreed values is less than the number of Byzantine. So if we see the figure, this area comes from Bouzy's paper, which is the theorem 1, and this area comes from our impossibility result, which comes from this theorem. And the proof, actually, it's a classical proof based on indistinguibility. And then, with the conclusion and perspective, we have proved that it is possible to solve T-resilience cassette agreements problem by a simple algorithm in one round in the following cases. So the first case is having a majority of corrects. We can do up to this value of set agreements, and if we have a majority of faulties, we can do up to t plus 1 set agreements. And we have also proved that if n minus t is less than k plus 1 and number of processes is less than 2t plus 1, which means that we have a majority of faulties, that there is no T-resilience algorithm that solves cassette agreements when the number of agreed value is less than or equal than t. And one of the perspectives is to find an algorithm or show the impossibility for the following cases. If the number of agreed values is exactly equal to this value, and if the number of Byzantines is between n over t and n over 2. So thank you for your attention, and for any further question, please feel free to contact one of the authors.